Arved Harding is a senior associate data scientist at Eastman Chemical Company in Kingsport, Tennessee. He has used statistical tools for 34 years to help scientists and engineers solve problems in R&D, manufacturing, technical service, and analytical laboratories. As a member of Eastman's Applied Statistics Group, Arvid has supported many areas of the company, including polymers, films, coatings, adhesives, and cellulose esters. Designing and analyzing experiments is one of many tool sets he has utilized. Arvid has been a user of Design Expert for much of his career, and as a member of Eastman's Applied Statistics Group, he has helped develop and teach classes in DOE, employing Design Expert as the hands-on tool for the participants. He is an ASQ certified quality engineer, and of course, he's been an active board member of the local section of ASQ for over 32 years. Arvid enjoys sharing his knowledge and experience with others. He also loves spending his time with his wife and 2 married adult boys and volunteering in the community. We are so lucky to have Arvid with us today. So I will pass this over to Arvid. Thank you.
So can you see my screens and hear me?
We can.
Very good. With that, thank you very much, Sherry, for that introduction. I have a little slide that I actually used to sort of introduce me, but given what she just read, most of that is on there, so not a lot of new news, so I won't spend much time on that. That'll be in the presentation if you want to look at it later for any reason. But also pointing out that where I'm actually from, and so you get a sort of a big picture. Since this is an international conference, you get an idea where I'm actually from. I'm going to try to get my laser pointer back I had a minute ago and see if that works. Yeah, I think that works. So originally, so Kingsport is located here, which is where I am now, physically pretty close to that area. It's where Eastman is located, and you can sort of get an idea in this North Carolina, Kentucky, Virginia, Tennessee area. They all come together in this area. I can be over in Virginia from here in about 10 minutes. I can get in Kentucky pretty quickly, North Carolina, all those things. So it's a very, very sort of central place nestled in the Appalachian Mountains. From Kingsport, I actually grew up in the Appalachian Mountains, in a town called Wise, Virginia, and went to a school that is now called the University of Virginia College at Wise. And it's about an hour and 20 minutes from Kingsport. Just giving you a perspective of where I'm from. Some of you may recognize some of the cities. Nashville is, of course, the capital of Tennessee, and it's about 4.5 hours away. So with that, I'll get started and introduce you a little bit to Eastman Chemical Company. This is our headquarters pictures you see. We are a Fortune 500 specialty materials company with 2021 revenue about 10.5 billion. So we're sort of a middle-sized, little small chemical company. When it comes to the big ones, we don't compare. We make lots of different materials. We are a marketer of advanced materials and specialty additives. We make a lot of plastics, chemicals, and fibers. And you interact with our materials on a daily basis, whether you know it or not. We operate 4 business segments. We have about 14,000 people internationally, serving about 100 countries. We started in 1920, so we just celebrated our 100th year recently when George Eastman of Eastman Kodak fame came and started our chemical company to supply chemicals to the photographic industry. And that's what got us started in 1920. So we have certainly changed and expanded since then. In 1994, we spun off, 93, 94, we spun off into our own chemical company and have been traded on the stock market since then. These are just an example of some of the types of materials that we make stuff into. And we don't make the materials you see, we make stuff goes into those materials, but won't spend a lot of time on that. You can spend time on our Eastman website if you're interested in that. You can certainly find out a lot about what we're doing now and a lot of what we make. Very diverse company. Gives you, as a statistician, it gives me a very big challenge to work in an area like this where I can support and work on so many different kinds of projects. I can spend time in some areas I'm supporting where I do a lot of mixture experiments, and I'll spend time where I do no mixture experiments. It just depends on the area that I'm in. Lots of different opportunities for different kinds of statistics to be applied. So challenging. It's been challenging me for 34 plus years now, so it'll hopefully challenge me for some more. So get to the nitty gritty here, and why you really came to listen to me, I hope, is to understand, we're going to talk about design of experiments a little bit, but we're going to talk about the responses more than we're going to talk about the actual types of experiments. You know, there's lots of types of experiments you can look at. Experiments will come in various shapes and sizes. And I'm going to move my camera slightly. I just remembered I'm looking at a different screen. I'm sorry about that. That may help you a little bit. I'm looking more at this screen in front of me now. So they come in different shapes and sizes, and you're familiar with all the ones that I'm laying out here, hopefully. If you're not familiar with mixture experiments, you'll see that later today. But also responses will come in lots of shapes and sizes. Typically, we take a single measurement on a sample. That's not abnormal. It's not also abnormal to take an average of several measurements on a sample, or an average of several samples taken at the same time. And another response, so we sometimes use a standard deviation of those measurements. So there's lots of different types. We could also have sensor data where we look at drop height, and when the sample doesn't break the height at the height that we tested at, we get sort of edited data, and we also have test values below a detection limit sometimes. So there's examples of sensor data, lots of different types of data that we end up analyzing. You can have obviously pass-fail data and other many different types, but also sometimes we end up with curve data. So I'm going to just give you some examples here, and hopefully you can relate to some of these examples. But one we'll be looking at today is a stress strain curve, where you can take the stress at various strain levels. You see in the picture an example of one of just cooling time against the water flow rate. And you see other examples include response over time. This is typically when you're studying patients, you want to look at how the response to a medicine changes over time, maybe. You look at viscosity as temperature rises. So here we got viscosity as a function of temperature. You have in sound, you end up with frequency response curve in sound that gives you, let's see how things change as the frequency changes. And in drug releases, we end up with dose response curves in drug development. So a lot of times we end up with the data is potentially there to give us, especially in our data technology today, to give us the curve, but many times we're not interested in the curve. We're just interested in a data point. We want to know maybe what is the stress at 1%, one particular level, or what is the dose response at a particular time. And we're not really thinking about the curve, but we are sometimes missing opportunities. And that's what I want to talk to you today about. I want to sort of open your thought process up a little bit, get you thinking about what you could do. Now, your clients may or may not be interested, may not need that information or want that information, but it's available. And a lot of times it's free. It costs you some time, some analysis time, but the data is there. Sometimes you have to figure out how to extract it out of the computer, but the data is already generated. So it's just a matter of getting the data and taking it to a new level. And that's what I want to talk to you about today. So here you're looking at an example. The example we're going to look at today is a very simple 4x3, 3x4 factorial experiment with 3 replicates of each. We'll talk about why we did that in a little bit. You can see these 12 different curves, 12 times 3 or 36 different curves. And you can see at each condition, so let me get my little pointer up here. You can see that at temperature, we have 2 temperatures, temperature 1 and 2. I can't reveal what those are, but temperature 1 and 2. So you have 40 degrees at temperature 2, while temperature 1 is at, and I can't see, it's behind something on me, but I think it's at 85. And so at 85 degrees, temperature 1 and 40, we have 3 curves, and so you can see how the curves vary. So there is variability in them. At this temperature in combination, the variability was a little bit less, quite a bit less, obviously. And I'm going to point this one out because he's going to show up many different times here. I'm going to call him run number 12, and you can look at run number 12 here, and you can see that this curve that I'm fitting isn't fitting real good. And you can see the points. There's a little deviation down in here. He'll show up quite a bit. This was one of the combinations at the highest temperature combination of both of them. And so what we have is we can sort of see, as you even look at these curves, just looking at the raw data, you can start seeing sort of how things are behaving. You can notice how, as temperature 2 changes, how is the curve changing? As we change at a given temperature 2, how is the curve changing as we change temperature 1? You can sort of get an idea what's happening and start immediately forming some concepts in your brain of what the model might want to look like as we go through. We'll continue talking about that. So before I get too far, I do want to acknowledge that this work was done. So some folks in actually our Belgium location, and appreciate all the work they put into actually doing the work. And I just helped out with a little data analysis. We have a couple folks at Stat-Ease. I'm going to show you how we used Python to actually fit these models, or at least I'll give you understand that's where the data came from, the actual parameter fits. And had Hank Anderson and Martin Biesner helped me with that. I needed help with that one. I am not a Python expert at all. I use many other packages, but Python is not one of them. And my son actually did some helping with me as well. So I appreciate all the help. And we have a whole group of statisticians, and we support one another very much. And I'm constantly being helped by the people around me. I need a lot of help. So let's think about this a little bit from what kind of information could we extract from this curve? So remember, we were really interested in the stress at 20% strain. But what if we could develop a model to understand how the 2 process temperatures affect the whole curve? What if we could understand which aspects of that curve are most affected by which variable? What if we could predict the stress strain curve anywhere inside our design space? And we could actually draw a predicted curve. And the predictions will be within plus or minus 0.005 of the actual stress value. Pretty cool. So what we're going to do, here's our process. We're going to take our data, we're going to think about what kind of curve we want to fit for each run. And we're going to use the same curve, same type of curve for each run, but the shape, the different parameters will change. We're going to then fit each run and save those parameters. We're going to fit the parameters as a function of the variables in the study, in this case 2 temperatures. We'll decide what the optimum combination of the parameters are, and we will draw a curve with the optimum set of parameters, and we'll go out and run those set of conditions and see how well we were able to predict. So here's the raw data. Looking at that, you get an understanding of there's a lot of variation. You see some clumps, some curves, so maybe there's some different variable settings here than down here. You can see things, the starting point down here at 0 is changing quite a bit. You can see as things go up and things. You could also see this, here's run 12. I told you he's a little different. You can see he's got some wiggles in here that the others don't have. He's also running lower than some of the others in some of the actual parameters. So what curve do we want to fit? You need to think about your process knowledge. You need to do literature searches, try different fits. I'm going to point out a couple of resources for you. Sometimes the nonlinear parameters of the model can be scientific information, such as rates and asymptotes and things like that, that could be very useful to the scientist. If nothing seems right, you could actually use spline fits. In today's computer world, we have a very available to fit splines, but this may not provide as much scientific information, but it could still give you useful visual how to move this curve around with these splines. That could be helpful. Functional data analysis is a branch of statistics that analyzes data providing information about curves, surfaces, or anything else varying around a continuum. So that side of things is something I'm just starting to get really into, but this is one aspect of it, what we're talking about. So with this data, I decided to use a 3-parameter exponential, very common nonlinear model used, and I use it many times. It's one of my first ones I start with. Sometimes it's an exponential decline, sometimes it's an exponential growth. So growth, as in this case, you can see what the model looks like, what the parameters that come out, and actually sometimes the parameters can be combined to mean something else. So you can the asymptote plus the growth rate actually equals your starting point. And the starting point is essentially the stress at strain equals 0. So right here, in this case, will be our starting point. There are going to be 36 curves, so I got to fit all 36 of them. I did put a resource in here for you if you wanted to look. If you go searching for nonlinear models, you'll find lots of resources available on the internet. This is one that might be helpful to you to get you started. So you've seen this picture before. This is the 36 curves fit to the data with the 2 temperatures. And you can see the variation. Again, there's run 12 standing out down there, and it will be taken out of our overall model fits. Here is the parameter table. This is the analysis table that I use. So we've got our X's and all of our parameters showing. And we also see I'm only showing 12 curves due to the size, but run 12 is down here, and I'll show you how it shows up as an outlier in just a minute. But also you'll notice a split plot structure of the data and a lack of randomization. I didn't have anything to do with that part, but we were able to overcome those issues with the split plot structure. Since we have 3 replicates of the whole thing, we were able to use split plot analysis. Felt pretty good about that, and that helped take care of any randomization concerns we had as well. So didn't feel too bad about the issue overall. The fact that we replicated everything helped with that. So that may have questions on that later. So here's the outlier look. So here's the individual fits of each. These are 3 at the same conditions. So this is run 12, 24, and 36. And you can see run 12 really doesn't fit very well, relatively speaking, compared to 24 and 36. So looking at that, this is where the statistician starts saying, something seems funny. And then you go back and talk to the experimenter, and the technician says, yeah, I got a note in my log. We had a problem with that run. Why didn't he tell me to start with? So we did find a problem with that one, and we have easily justification, statistical and otherwise, to take it out. So we took that one out and continued on with our analysis. So how good do the models fit? Well, they fit pretty doggone good overall. This is just an example I pulled out. These are 3 fits of exactly the same conditions. The temperature at 85 and 70 runs 2, 14, and 26. And you can see how the data fits. Looks pretty good. Now, if you blow that up by looking at the residuals, you can see the R-squareds are super high. But let's take our residuals. And so these are the residuals of those. So one thing you notice on the residuals, there is some systematic error. There's some systematic error in the sense, if you look at here and in here, you're a little running high, and over here on the end. And I agree, there's still some systematic error there. It's not a perfect fit. But I will point out that is predicting within plus or minus 0.0015 on this scale of the stress scale. So that's pretty doggone close. So while it's not explaining it perfectly, and there's still a few things going on, and there might be a need to dig deeper, the scientists may have a need to dig even deeper than that. It seemed to give us good enough estimates for what we were trying to do in this work. So felt good about that one. All of our R-squareds and our fits were greater than 99%. So felt like that this model tells us pretty good what's actually happening, as best as we can tell. So I started out plotting the exponential parameters against one another. I like to look at my y's versus my y's, my x's versus my x's, my x's versus my y's. etc. And I started my Y's versus my X's, and you can see in this, that's run 12. It's standing out, as we pointed out several times. So we ended up taking it out. You can also see the effective temperatures here. This is the blue in the is 40 degrees in temperature 2, and green is 70 and 80 degrees. We had some 70s and some 80s, and we had some hundreds, and that's the reds. So we can sort of see that quadratic behavior in temperature 2 that we'll end up with respect to some of the responses. And I'll quickly gloss over that part. It's not as interesting or useful, but you see that outlier coming out a lot. This is actually showing the starting point versus the stress at 20 degrees C, which again was a primary response of interest. And you can see that point again was an outlier even there. So I created this plot, and it shows you, if you look at the, again, this looks similar to one I had earlier, but you're looking at now 85 degrees for each of the actual responses. So I've got temperature 1 at 85, temperature 2 is down here on the x-axis. Get my pointer back over here. There we go. Temperature 2 is down here, temperature 1. So at 85, as I change temperature, this is what it looks like. So this is a quadratic fit to the asymptote response. And we've got different responses. I'm going to go down here, even down to the stress at 20% strain. We can see a little bit of a quadratic, not strong, not as strong as some of the others. But you can start to see some of the effects. And again, I like to use this to start thinking about, what is my model going to look like? What do I want to put in my initial model? So I'm going to start thinking about, well, I certainly need an effect of, I can see the effect of temperature 1. That's not a problem. I can see the effect of temperature 2. But what about interactions and quadratics? Yeah, I have a need to put some quadratics in. And may even have, and I can see it up here in asymptote especially. Look, it's getting a little straighter as I go out. So as I increase temperature 1, the quadratic effect, get my pointer back over here. There he is. As I increase my temperature 1, the quadratic effect of temperature 2 seems to change. That's going to show up when we start thinking about this interaction, temperature 1 times temperature 2 squared. That may not be a conventional term you're used to looking at in your models. And a lot of people talk about these kind of terms and say, I don't put those in my model. I don't look for them. And I have a saying that says, you don't find stuff you don't look for. Some people say, I never look for 3-factor interactions. And I say, have you ever seen one? They say, no. I said, have you ever looked for one? I said, well, no. Well, it's hard to find something you don't look for. So sometimes looking at these kind of plots initially can open your mind up to extra terms in your model that might be useful. And especially when you start seeing lack of fit being significant, then these kind of things might show up if you'll look. And sometimes your VIFs, sometimes your data may not be structured well to model them, and your VIFs might not be good, but you might want to take an initial look at least to see, and that might help you in future designs for that. So again, looking at each one of these responses, you start getting a good understanding of how things are going with things. Let's see, there we go. So I did use the split plot approach. So you'll see a whole plot model and the subplots, and these term interactions and higher order interactions are in the subplot. We did reduce the model as appropriate. All models had R squared of greater than 93 and R squared adjusted to 92, and transformation was considered but not really needed, especially when I added this AB squared term in. So I'm going to switch over and do a little bit of live demonstration. I'm going to attempt to and show you a couple things, and we'll come back to this and look at the results. So the first thing I've got is just my raw data set. This is the raw data of, I haven't got the parameters in here yet. So I'm going to show you with respect to using the Python that I mentioned. And then I will get into some of the design expert issues. Actually, I'm using a Stat-Ease 360. Many of you know that Stat-Ease 360 is design expert with additional capability added in. And part of that capability and what I was able to take advantage of is the Python edition. So I'm going to open my Python script editor, and I'm going to open my Python file that was created. And so now we see I have a Python code written that will help me. And what this does is models my raw data. It's modeling my raw Excel file. Let me get that open for you. I think this is it. Pull it over to this screen. So this was my raw data file. And you can see for each temperature combination and each replicate, I have a lot of stress strain data. That's the raw data. So what I'm going to do is fit the curves. I'm going to fit stress versus strain for every one of these combinations. And I'm going to use Python to do that for me. I'm not going to get into the actual coding. I'm not a Python expert, as I said, and without the people at Stat-Ease, I couldn't have done this. So I am going to run. I think there's a run button here somewhere. I'm going to run this. So if you'll be patient, it takes a little bit of time to fit those 36 models, but not too much. There we go. Get this out of the way. So what it did, there's my 36 curves you saw, and blow that up, it looks a little better. And if I close this, actually, I'm going to go ahead and close it because it's going to then generate another curve, which is turns out to be the optimal fit. We'll look at that later. And over here, you can see the actual parameter estimates that were created from the output. And it also created for me a data set. Now you can see in the background here, we now have a new data set where it has taken the X's and added my 3 responses in. And so did that for me pretty automatically, which was great. With that, I'm going to pull out my analyzed version of that. And I also added a couple of responses like the starting point, which was the sum of the asymptote and the growth rate and the stress at 20% strain. And I have analyzed the models and reduced the models accordingly. I'll just show you a little bit about that before we get into it. So I went ahead and there's my whole plot and subplots, and the terms, let's see, should have reduced that one. Let's see, get that one out of there, the A squared B. So that is what that model looked like. And then I produced graphs from those, looking at my contour plots and other things. So I've got some of that in my PowerPoint slides. I'll go back to my presentation. And let's take a look at that. Here's the coefficients table that shows you for each response which terms were significant. You see some grayed out ones. The terms were not significant that are grayed out using a p-value of 0.5, but they are in the model because a higher order term involving those are in the model. So AB is not significantly important, but the AB squared term is. Therefore, we kept that in the model. That's called hierarchy. And we followed that in fitting these models. So you can see that again, lots of other model information available, but I just wanted to get you started looking at that. Then we developed the, remember we wanted to maximize the starting point parameters as well as the stress at 20% strain. So originally it was just 20% strain, but we thought if we can maximize that starting point, which again is a sum of 2 things, it's a sum of the asymptote and the growth rate. So we're actually sort of maximizing them. And if you remember also back into when we was looking at responses, how they correlated with one another, there's a correlation among all of these responses. So I then took and reached a area here. You can see I could be around 85, 58 or so, and a lot of different numbers are close to that. This sort of gives me a general idea of where I want to operate. I'm going to then look at my optimum area here. And you can see that generally, if we look at the here starting point, it's looking over here, to maximize it comes out about 0.01. So some of the numbers are negatives, so you can actually get above 0, the starting point, and that pushes it up where it starts. And the prediction at 20% strain, the stress at 20% strain is around 0.07. Again, that's pushing that number up, that asymptote up, pushing that number at 20% strain up. The asymptote is also going up to 0.09. We can see that. So that is the area. And a wise teacher told me long ago that if the optimum is in the corner or the optimum's on the edge, then the optimum's probably not on the corner or on the edge. So keep that one in mind. There's some better operating areas over here somewhere. There may be reasons we can't drop below 85. We may be limited in our process conditions or limited in the chemistry, but certainly something to consider, because it looks like if we were over here somewhere, we could be better. And I'm not going to predict over there because I'm not extrapolating. I don't think these models would extrapolate very well at all. Not interested in doing that, but I'm interested in at least potentially recommending that we explore some areas over. We might want to go over here and design an experiment somewhere in this area where we go maybe from 70 degrees to 85 degrees. And let's take a look and see how things change when we get over in there. Get an understanding. So this has moved us to a better understanding of where to operate. We can then take those conditions, which I did, and actually then draw a curve at those conditions. What is the actual curve look like? And that's what it looks like. It's nothing exciting, and but it does have a starting point above 0.01, which was pretty high compared to many of our starting points. Actually, it was among the highest. But we didn't have any conditions any conditions at 85 and 58. We had a condition close by. We had 85 and 70. We actually had 3 runs at 85 and 70. So that's the closest we had at 85 and 70. And we can see that that starting point was indeed a lot lower than our 0.01 over here. And we're 0.014, I think we're predicting here. So we can get a better starting point if we can just drop, maybe keep it at 85 temperature 1, but drop temperature 2 from 70 down to 58 or so. So there's some new operating conditions. So ideally, you would run these conditions and see what happens. We did not do that because of the change in the priorities of what we were working on, but we certainly learned a lot about what we needed to do in the future. And we're taking advantage of this knowledge as we're working forward. So our learnings. His original response of interest was our stress at 20% strain. But if you think about the power of the curve, we can learn a lot more than just the original objective. There's a whole lot more information here. With this knowledge, we now have power over that curve and can change the shape. We can change the starting value. We can change the asymptote. We can change the stress at 20% strain, whatever we want within our design space. And I emphasize that importance. That designing your experiment and learning what's going on inside, so revealing. It's like getting to the mountaintop blindfolded, or somebody dropping you on the mountaintop, or somebody dropping you somewhere and then you look around. I live in the Appalachian Mountains here, and I just enjoy so much climbing the mountains, walking the mountains. I don't do much climbing, I walk. Get to the top somehow and just take a look around. Sometimes I drive, most of the time I drive, and just look around at the top of those mountains and see what's around you. And that's the power of doing DOE and on these kind of things, is being able to learn what's happening around you and be able to get a good look at that. So with that, I will stop and see if we have any questions in the chat.
Thank you so much, Arvid. We just have a couple questions, so if anybody has more questions, we're going to have time for them. Go ahead and type them into the chat, the questions panel. So question number 1, going back to that run number 12, did you happen to go back and predict it with your resulting model and rerun it to validate?
We did not do that. We had 2 other runs at those conditions, remember? So yeah. we already had data that validated. Plus, we had data from the actual experimenter who said there was some reasons that one didn't work.
Yeah, that makes a lot of sense. We have a user who is new to split plot design. So what is the benefit of having different groups or blocks in the design? Do you want to talk about split plots just for a few minutes?
I'll talk about it a little bit. I'll also give you some references. One I'll give you is yesterday's talk from Paul Mullinex. He did present some basics on split plot in his talk yesterday. So you might want to go look at that one next week when it comes available to you. You also want to go look at the Stat-Ease tutorials on split plot, and they have two or three tutorials on split plots, and there's also several webinars out there that Stat-Ease has put out that explains a lot better than anything I'm going to say about the split plot concept. But the idea is the fact that you have not randomized your experiment. So because you haven't randomized your experiment, you can't treat it as really randomized. And I'll go back and show you sort of this. So you've got 85, it was ran this way. So they ran 85 degrees at temperature 1 while they varied temperature 2, and etc. So if we treated this as 36 independent runs, we're treating it as 36 independent random runs, and they're really not. They're running groups. And so to treat them that way helps the statistics to be treated more correctly. If you only did, just a good example of that, if you only did 12 runs, then you would be treating these 12 independently. If you said, I'm going to analyze these 12 runs and treat temperature 1. But really, in reality, you only have 3 runs of temperature 1. You have run at temperature 1 is run at 85, 95, 105. So you don't have all those degrees of freedom for temperature 1. You really only have 2 degrees of freedom because you've only changed it 2 times. So with that in mind, you're cheating the statistics. So you can do it. The program won't know any better, but in reality, your conclusions could be wrong. You could be misleading. So the split plot analysis is very important part, and it has been, and I will admit, in my 34 years, I've done many analyses wrong because I was ignorant of split plot analysis and I didn't have the tools. That's no longer an excuse. My ignorance is no longer an excuse. I'm better educated, and I certainly have the tools. Stat-Ease has made those tools available to you to help it make it pretty doggone easy to design split plot experiments and to analyze them. Now, a lot of times we design split plots because we are in a situation where we can't really change that temperature randomly, but changing it a couple times is not too bad. In this case, we end up, instead of changing it, maybe potentially if you randomize 36, maybe you end up with 25 changes or something. In this case, we ended up with, out of 12, I guess 12 changes, you end up with 11 changes or something like that. So a lot less, and that can save a lot of time. So there becomes many reasons we would not want to randomize a variable. We call it a hard to change variable, and that's okay. But now we got ways to deal with it. I've actually designed experiments that were 3 times larger than the randomized design, but a half time faster than the randomized design.
Thank you. Appreciate your comments there. Okay, so let me read this one. Did you try decomposing the original runs into functional principal components, FPCs, and then fitting the FPCs and using this model to optimize? I suspect that Python can break the curves down into the FPCs. I wonder if you would get to the same result as modeling the NL parameters.
And the answer is yes, I did do that. So that in functional data analysis, platforms, you can do that. And I have done that in many different projects. The reason I'm not a strong proponent of that is trying to interpret, and you do get the same results, but interpreting is not the same. What does it mean when you start talking about those principal components? Trying to break those out into what they actually mean, you're lost, because there's a linear combination of all the variables. And so you can't really tell what's going on very well. But what you can look at here is I can tell you what the asymptote means. I can tell you what the growth rate means. I can tell you what the starting point means, and they can be scientifically very, very valuable to the scientist. But I can't tell you what those 3 or 4 principal components mean. In a sense, it's a lot harder. The interpretation of those models becomes much more difficult than these models that I've described. And so that's why I'm a stronger proponent of doing this. I like doing both and make sure they do agree. And if I start learning one in the other one reveals more information to me, I'm certainly willing to use it, no problem. But this one is easier to use. And there's actually ways you can sort of combine the 2 concepts together. And I did that too. And in some software, you can do that. But I think being able to just get to this point is a step in the right direction for most people.
Great. Regarding the model reduction that you do in general, do you prefer backward regression over forward or stepwise, or what are your thoughts on model reduction?
It depends on to me, it depends on how complex your correlation structure is among your X's. If you have a strong factorial that it's not going to really matter very much, you're going to reach the same. But if you've got some complicated correlation structure, and in my case, I had some ABs, AB squareds, and things like that. So I like to use a backward p-value in most DOEs, but also use a forward AIC. And there are many other techniques you can use. And I use at least those 2 and see if I'm coming to the same model. And if I am coming to the same model, then I'll usually accept that. If I'm not coming to the same model, I'll wrestle around with it. So I always recommend use more than one procedure, especially if you got a bad VIF structure, then you probably want to use something like forward AIC and or forward BIC. I prefer AIC most of the time, but I use AIC to come up with some kind of a model. But when I'm dealing with good DOE, a backward p-value works as good as anything.
Great, thank you. To the audience, are there any other questions? We still have time. Oh, a very long one came in, so hold on 1 second.
No problem.
I have to pull this up. My screen is small.
I'll put my listening ears on here.
Okay, let me see if I understand right what you did. You set up a 2x2 experiment with 2 factors of temp 1 with 3 levels and temp 2 with 4 levels. You
so
measured
a 3x4 experiment, not a 2x2.
Yeah, nomenclature there. 3x4. You measured a curve at each of the 12 DOE factor combinations with 3 replicates, resulting in 36 curves. You used Python to fit the 36 curves and output several values that describe each curve. These several values, like asymptote, scale, growth rate, etc., became the responses entered into Design Expert. This is where I start getting a little lost. Do asymptote, scale, growth rate have meaning to you? I don't see how one value of, say, asymptote is more desirable than another. Could you talk a little more about what these responses mean? Thank you.
Very good. Great question. Yes, your procedure you had is exactly correct. And so I'll go back in my slides here to about here, I guess. So, or even thinking about which curve to fit. Let me find that slide here. Okay. So the asymptote, scale, and growth rate to a statistician, they might not mean a lot, but they do if you understand them. But to the scientists, they can mean a lot more. So remember the asymptote plus the growth rate is the starting point. So at mean strain of 0, where's the curve start? So at where there's no strain, what kind of stress is the actual sample under the specimen under? And when there's no strain whatsoever. So there is a little bit here, and it's some of it, you might want it to be high at 0 strain. You might want it to be low at 0 strain. It depends on your objectives that you have with this. And this is a plastic of some kind, I can tell you that much. So what kind of objective you have on plastic? And Then your growth rate, how fast is it going to grow, is your growth rate. And then your asymptote is where does it level off asymptotically? It's asymptotically approaching some value. Again, that's very related to the strain at 20 stress at 20% strain, because the higher the stress at 20% strain, the higher the asymptote is going to be. So they all, yes, these parameters do mean something, and they can be interpreted. So one asymptote is different than another asymptote. They can mean something very much so. And again, if you go back and think about some of the other places I mentioned you could do this kind of thing in, each time you can develop different curves and different sets of parameters, and they will mean different things to the experimenter. In the example you're seeing on the right, the cooling time, you can see how the cooling time asymptote is going to approach as at 0 or at 5 is the lowest value, but there also you can predict what's happening at 0 or what would happen as it gets close to 0. It's actually, it looks like it's never going to potentially reach 0. It's maybe asymptotic on that side of things as well as asymptotic on the low side. So these things, these curves and these parameters to the scientist many times are very, very meaningful and can lead to new discoveries that just fitting models to them without paying attention to the types of curves that we have, you can lose a lot of information. I'll put it that way. I hope that was adequate, and if the person who asked the question did not feel like I answered adequately, please type in something else.
Oh, I think that was good. Thank you. I'm not sure I understand this next comment. Maybe we can figure it out. A and C have different units. How can they be added?
A and C are asymptote and growth rate. How can they be added? They're not in different units. They're in stress units. So they're all, it's just the level, the asymptote is the level at which the stress at which it approaches 0, or excuse me, it approaches the level at which it approaches as the mean strain reaches infinity. And C is the growth rate. So I don't think they're really in different units. They're both related to the stress. So they are additive according to the theories. This is what the theory told me. I didn't make that one up.
Okay, are there any other questions out there? Let's see, do you also use this technique with using NL models with mixture experiments with, say, 5 to 15 formulation components? Does it work as well?
If your design instead of a split plot is a mixture experiment, then absolutely. And so it wouldn't change a doggone thing to me if you replaced this factor 1 and factor 2 with 4 mixture components. Wouldn't change a thing.
Great. Well, Arvid, I think we are going to close out your talk. And I want to thank you very, very much for all of your time here with us today. This was a fascinating talk once again. And so thank you very much for being with us.
Thank you again for the invitation. I hope this was useful to people. And if someone has specific questions, are welcome to email me at aharding@eastman.com. I'll be happy to address any concerns or questions you have.
Great. Thank you.